Data Skeptic mini-episodes provide high-level descriptions of key concepts related to data science and skepticism. Our topic for today is Dropout.
In order to talk about Dropout, we're going to have to build up a few details, make sure you got the background. First of all, we've talked a little bit about overfitting. We never explicitly did an episode on it. Do you know what overfitting means?
The model is too closely linked to only one output. It is too narrow.
That sounds like a very good answer, but I'm not entirely convinced you know what it means. Well, one way I like to put it, and this isn't necessarily the most perfect explanation, but I like to think of overfitting as memorizing your training data rather than learning the underlying features.
It's only one size and only fits one person instead of a lot of people.
Yeah, that's a really good way of looking at it. In machine learning, what we want to do is really learn the underlying correlation of the data between the input data and the output. Of course, you could do that accidentally by looking at little artifacts and nuances. Like if in your training data, if it was a data about people, and you only had one person named Paul, then you might conclude, well, everyone named Paul gets labeled to a certain class just because all the Pauls you've seen, which is only one, end up that way. But probably that's not a useful thing to do. Dropout is most prevalent in neural networks, although it does appear in other places and other types of algorithms. We haven't really talked much about neural networks or deep learning, even though we're going to be doing a lot of topics on that in 2017. To touch base, do you have a sense of what neural networks are?
Networks in your brain.
That's awfully close, yeah. Neural networks are these sort of data structures that are inspired by what we know about the brain. They don't necessarily correlate exactly, but that's where the inspiration comes from. That, the brain is made up of what?
Cells.
What are the cells called?
I don't know what they're
Neurons?
called. Oh, neurons.
So neural networks are very popular, in particular deep learning, which is just a type of neural networks, very popular in image recognition. Have you noticed that computers have gotten really good at dealing with images?
They've gotten better.
Only better? They haven't gotten awesome? They're now beating human accuracy in some tests.
What are the tests?
Like identifying objects in a picture.
Humans can't identify an object in a picture?
Well, this is actually be an interesting topic for another discussion. Yes, humans can, but humans are almost no longer ground truth. There are cases where humans will give different answers or fail to notice things. Like if you're like, how many joggers are in this picture? Sometimes people will make mistakes.
Yeah, I could see that.
Mm-hmm. When it comes to recognizing an image, how could it be that a computer is looking at an image and understanding anything? Do you have a sense of how that might take place?
Well, it was trained on some sort of data earlier.
Yep. When it comes to image data, you've worked a lot with raw files. You know your file formats, right?
I know some.
What is the sort of unit of data in a file format?
Most people say pixels or DPI.
Yeah, pixels are the key. So actually, in a lot of machine learning tasks, what we do is we take the intensity of a pixel, and we convert that to a numeric value. You could very quickly see where I could make a program that can determine whether a photo was taken at night or during the day, right?
I don't know. I guess it would only work if the photo was taken outside. If it's indoors.
Sure, let's say it's all outside.
Well, the easiest is that you could say if it's taken at night outside, it's probably likely to be dark.
Yeah, so while this might not be a very generalized solution, you could look at all the intensities, and if they're all on average very low, it might seem like that's a nighttime photo. If they're all very high, probably a daytime photo. That's a very trivialized basic case, but that gets you the idea. That you establish all these neurons, their inputs are the intensities of all those pixels. And then the outputs might be, a classification of some kind. Is there a jogger in this picture, yes or no? And you only want the final layer of neurons to say yes, if in fact there are joggers in the picture.
You said it was between black and white. There's a 50% line. It was on the 50% line. Would it be black or white?
Well, that depends. That's the whole secret to neural networks. You want to find where is the best line to use. For example, in my very convoluted idea of can you detect if it's night or day, maybe it's around, 30% intensity. Above that is more likely to be day, and below that is more likely to be night. But actually, forget that I said 30%. You just want to mathematically determine what is the optimal value given the training data. And then you want to use that in the future. Does that make sense?
Yeah.
Those input layers, you want to find what I will call the magic vector of weights, that you multiply all the inputs by those weights and they give you this output, which is very useful. And the whole trick is, well, what are the best possible weights? Another way to think of this is maybe like if every neuron is a different person giving you advice. How many people in your life give you advice, whether you want it or not?
I don't know. You mean you want me to count how
just
many
a
people?
guess, yeah.
I don't know, 5.
Oh, that's that few?
Well, who's giving you advice? You have a team of 30?
Well, no, I mean, like, you could be, like, riding your bike down the street and somebody could be like, stay on the sidewalk.
That's not advice. That's like a complaint.
That's a form of advice.
No, I consider advice something that might actually be helpful. Someone who's just like driving and they flick you off, that's not advice.
Well, so good point. You learn to ignore that person, right? So the weight you put on their input is 0. You start ignoring them, I assume, right? Mm-hmm. So the process of creating a neural network is all about finding the right appropriate amount of weight to put on all of the inputs you're getting. In other shows, we'll talk about exactly how you do that, because there's a couple of methods. But what I want to talk about today is dropout.
What is dropout?
Let's do another contrived example. Let's talk about recipes. Now imagine if you were trying to, from a recipe, determine what the dish is. Mm-hmm. And I said, hey, Linda, the ingredients are beans, rice, cheese, and a tortilla.
Either a burrito or a quesadilla.
All right. So your input layer would be like the presence of every ingredient. Is there rice? Is there lettuce? Is there a tortilla? And so on and so forth. And you could imagine there's lots of inputs because there's lots of possible ingredients. The output would be some label, a flag that says it is a burrito, or it is jambalaya, or it is polenta, or who knows what, right? And so your job is to find the right weights when multiplied by the inputs that tells you the correct dish.
The right weights? Mm-hmm. Weights of what?
Weights that you put on the neurons.
Okay, so your goal is to find the correct weights. Then mm-hmm. What'd you say?
Where when you multiply the weights by the inputs, you get the desired output.
And the inputs are, what's an example of an input? Rice?
Yeah, it would be like a 1 or a 0 if there is rice present or not.
So you would say, so I'm confused. Can you make up like an equation for me? Because sure. I don't understand this at all. Sure.
So let's say X, Y, and Z are your inputs. X is bread, Y is cheese, Z is ham. And then we're going to have weights W1, W2, W3 that each get multiplied respectively by X, Y, and Z. And then you're going to sum all those up, all right? And the output, if it's 1, we'll call it ham and cheese, and if it's 0, we'll call it grilled cheese. So the smart thing to do would say weight 1 is 0, and weight 2 are 0, and weight 3 is 1. So then if it only comes out 1 if ham is present, in which case you multiply by 1 and you get 1. If ham is absent, 0 times 1 is 0.
I don't understand where these numbers came from. You made up W1, W2, W3.
Yes.
And then where these numbers come from.
So the W's you have to figure out. That's the whole process of finding the optimal weights. And we'll talk about where they come from in a later date. For now, let's just assume we have some very tricky process of computing the best possible values. Now, do you think this is a useful way of determining the type of recipe?
For me, no.
Right.
I would just figure out if it has ham or not and move on with my life.
Because you're able to look at this at a higher level of abstraction. You understand a lot more about recipes and what comes together. And ultimately, that's what neural networks do by having hidden layers. So a hidden layer allows you to create like an intermediate representation of the data. Hidden layers in the middle allow you to multiply and develop these middle level representations. You could have something that's, let's say, flour and jelly could be in something, and that's kind of vague. But as soon as you say there's also peanut butter, now it seems to imply it's probably going to be peanut butter and jelly sandwich. Whereas without the peanut butter, it could be a wider variety of things.
Are these rules just like, if there's peanut butter, it's American? That's it? Is that your rule?
Not exactly, but
I don't know what this hidden layer looks like.
It looks a lot like the other layers. Like I wrote out that equation for you, that, X times the weight. That gets you to some set of outputs, and then you would have the same process in the middle, multiplied by another different set of weights. But peanut butter is a good example to get back to our core topic of dropout. Yes, it's true that dishes that have peanut butter tend to be American, but is that universally true? Don't Canadians like peanut
sauce?
Butter? Oh, yeah, peanut butter sauce. You have a great recipe for a peanut sauce. Would you call that an American recipe?
No.
Okay, so if we were very naive and we just said the presence of peanut butter implies American cuisine, we would make a lot of mistakes. But in neural networks, that can happen. the system, in trying to do its very best to figure out how to classify things, it might latch on to something like peanut butter and be like, oh, in all the recipes I've seen, peanut butter always seems to be an American dish. And that's just because it hasn't seen enough examples of non-American dishes that use peanut butter. Probably because they're rare. It would be like naive to depend too heavily on that feature. And actually, it might start to ignore other features. If it says like, hey, every time there's peanut butter, it's American, it might not look deeper into the data and figure out that, well, there are other things to learn about what makes something American cuisine or not. So Dropout is this cool idea to help prevent overfitting, where you randomly pick some of the neurons and you just set them to 0. You kind of like hide the information. And then you ask the network to solve the problem the same way. The problem is like a little bit out of focus every time. So it can't overfit the data as easily because you're hiding some of the data each time. It's a little bit like going back to my advice example. If you were like some chairman of the board somewhere and you had a bunch of people giving you advice and you started to rely only on a single person, you would start to overfit to their answer. And if they were ever wrong or not there, you'd be lost. But if you randomly had some of the people on your board call in sick days and you couldn't always get their advice, you would have to learn to get a more variety of a representation of advice from the rest of the people. And that's the core idea of Dropout. So I think my best analogy tonight was the chairman of the board example.
Chairperson.
Chairperson of the board, that's right. Or in your case, chairwoman. If you started relying too heavily on one of us, even if we're right a lot, maybe I'm always giving you good advice, I don't cover all situations. So from time to time, you might just want to ignore my advice so that you have to learn how to synthesize the advice of everyone in a better way and get a more generalized solution.
Mm-hmm.
So Dropout, you do that by stochastically setting, a bunch of these of your neurons to 0. Usually about half of them seems to be the best number in practice. That's always worked well for me in most cases. It seems to be what everyone else is doing, but I don't know much about fine-tuning. Are there situations where you'd want something a little bit different from that? But yeah, basically you set some percentage or some likelihood of dropping out a neuron, and then you try and learn with that flipping neurons on and off as you go. And it tends, in my experience, not to make the learning take too much longer, because in training neural networks, the problem is always how long they take to train. There's a heavy computational process. But Dropout doesn't seem to hurt that very bad. And what it does do is it makes you less likely to overfit, whereas overfitting you might only detect after spending a long, long time waiting for your network to converge, You come back the next day and it's done, and you're like, oh shoot, I overfit and I didn't even know it. Got to start over from scratch. So Dropout helps with that.
I mean, but I think like this technique of blocking something out to see the bigger picture is an important one that people can take away in life.
Oh, you think this could be applied in sort of an abstract philosophical way, huh?
Well, yeah, I mean, today on the news, I mean, not today, but generally in the news, there's a lot of news about like white cops, black cops, killing black people, killing white people. And it's just like, okay, are we getting too specific? What if we just blocked out their race? How would this story read?
That's interesting, yeah.
Or like sometimes there's like just conversations and you wonder if you were to swap the genders, how would it come across?
Oh, that's clever. Now I see why you brought race into it and stuff. Yeah, your instincts were better than I understood. That's right. Leave out some important detail. Not to say that it doesn't matter, it didn't affect the situation, because certainly race plays a role here. But how does the story read absent that detail? You might learn a more generalized solution for why the problem exists.
Yeah.
And then sometimes, of course, it will be there, so you will learn to rely on it, but not over-rely on it to explain the circumstances. Oh, well done, Linda. That was a nice contribution.
Well, maybe that's the point of the conversation. But yes.
Now, I notice you still haven't gotten a new picture of our T-shirt for the website.
You haven't given me a T-shirt. You said you were going to iron it for me.
I don't think I said that.
You did. You said, I'll iron it for you and give it to you.
These shows are recorded, right? We can go back and check.
You said this in the house when it wasn't recording.
Well, that's all purely off the record then. All right. Well, thankfully, despite the awkward picture of the T-shirt hanging in our kitchens, people are still picking up our amazing T-shirts. We're sending them out like hotcakes, and get yours now because they're very stylish and
they They look better on than in the photo.
Yes, indeed. So if you'd like to support Data Skeptic, why not head over to dataskeptic.com and get yourself a t-shirt. We go from extra small or extra small up to, I think, 4XL. So I imagine we've got most people covered.
Literally, figuratively.
Indeed. And we're doing a lot more stuff on the dataskeptic.com blog. So head on over there whenever you're done driving or commuting or wherever you are. And between now and then and thereafter, please keep thinking skeptically of and with data. Good night, Linda.
Good night. For more on this episode, visit dataskeptic.com. If you enjoyed the show, please give us a review on iTunes or Stitcher.